Hello everyone, hope you're having a good time. This video I'm going to talk about how to use scratchANN library in C. This is a library I created which we can develop artificial neural networks, specifically with multi-perceptron architecture. It has all the features, not all the features, some of basic features that other artificial neural network packages have also on Python. And then after running a test case, we're going to compare the result with the same thing we have on TensorFlow. I developed this library on C. For some of my students, they wanted to develop artificial neural networks from scratch in C, and they were wondering, just let me see if I'm recording. Yes. It was a little bit difficult, challenging for them to develop it from scratch. So I was thinking maybe I can create, share my codes, create the basic ones, and then in the future, if they want, they can work on that. This is a little bit challenging topic. You need to know C programming, dynamic memory allocation, memory management, pointer, reading a file, quite most of the things necessary to do a scientific programming in C. Then also you need to know a little bit about the basics, at least the basics of artificial neural networks. If you don't know where to start, you can read this book I created. You can find this book on my GitHub. And after, if you know the C programming, which is good, you can just skip to this chapter, which I discussed the basics of artificial neural network and multi-layer perceptron with one single neuron, then more neurons, and essentially the general format programming something like this, and then also how we train the model. Essentially, I guess this section we're gonna have some examples. Then you're gonna see this section, introduction to scratchANN, and then in this section we're gonna have multiple test cases. One is energy efficiency dataset, which I'm gonna do in this video. Then probably next videos I'm going to talk about another case study, breast cancer dataset, and also we have another one which is MNIST 784. It's an image classification problem. We're gonna have different set of data set. We're gonna try this scratchANN in different data sets to make sure this scratchANN is efficient enough, and then we'll compare also the results with what we have on Python, with the libraries we have on Python. Specifically, we're talking about TensorFlow. The files, you have the files here, some of examples here, but first let's start from the example, the demo we have here. You have a make file, you have a demo for a specific example. This is the place I have my int main, and you can check out the file. This is a bunch of inputs you're going to give for the specific data set we have, and then we're going to talk about the details a little bit more, then calling the necessary function to train a model, save the model on the hard disk, and in the future if you want to retrain the model or use the model, you need to load the model. So this library this library covers the basic functions you need to train a basic model, basic multi-layer perceptor. It supports if you want to customize the layers, number of layers, number of neurons in each layer, you can do that. You can have mixed activation functions in each layer. Specifically in the output layer, it's really necessary to have multiple different activation functions, because sometimes you have a data set which one of the targets is continuous, the other one, let's say, is a binary or classification. This library allows you to do that. At this moment, it supports these activation functions. In the future, you can of course develop it. It has also basic implementation of prior computation, which also we covered the same thing we have covered in our lecture notes for our courses in section prior computing. At this moment, it has only SGD optimization algorithm. Again, in the future, if you want to develop the code, you can develop more advanced optimization algorithm like Atom, or even try more global optimization algorithms. In our courses, sometimes I give students a project developing global optimization algorithms, for example, PSO or genetic algorithm. You can integrate those optimization algorithms to this library to have also a global optimization algorithm to train your model. Now let's go. After downloading the files, you're gonna see these files in your directory, the same files we have here. Just maybe I can open it in VS Code because I have it actually here. This is the demo. Of course, I needed to include some of the libraries necessary. One of them is scratchANN, and scratchANN is actually the architecture, the definition and the structures of the multi-layer perceptron architecture, some of activation functions, and some of the functions we need to use to train from pre-processing, basic pre-processing the data, training, creating model, and then training the model, summary of the model, train how many trainable parameters it has, kind of the same functions you have also on Python, TensorFlow, saving your model on the hard disk, and then in the future, if you want to retrain or use the model, you don't want to waste your time training your model and then just, you want to be able to save the model. Let's just start with the demo. First, you have a bunch of inputs. We're going to talk about the inputs. You need to know the basics of artificial neural network before watching this video. Again, I'm just keep saying that because I know otherwise it's going to be difficult to understand what each parameters actually means. The architecture of the each layer, and essentially if the data needs, let's say, to be shuffled, reading the data first of all, if the data needs to be shuffled, and then splitting the data into train and validation. I call this validation, but it's actually test data set. It's not validation. Creating the model, training the model, saving the model on the hard disk, and then freeing up the memory. And if you want to load the model, you can load the model, and then you can retrain the model which you just loaded, and with new settings, with new data sets, it's up to you. And then freeing the loaded model again, deallocating the memory for the data set. Let's go to the top. Let's talk about the data set we're gonna try to create a model to train on those data sets. The test case in this directory I have is a data set called energy efficiency. Okay, it has 8 inputs and 2 targets that the neural network needs to predict. The number of the data set you have, this is the Python code I used to download this data set. If you want to, you can just download the data set here, or you can use this Python data set, this Python code to download this data with this specific format. Every column is separated with a tab space. We have a function to call to read the data. Let me just open this one. You have a function, actually it's here, called read data from file. The way this function is written, I organize this data, I download this data in a way that this file, this function can read. I created a separate source code for this function implementation, because I wanted to say it's kind of separate from the library itself. And in the future, if you can change this read from file in any way you want. Let's say you want to read it from Excel in another format, you need to change this implementation here. Right now we're keeping that simple. We're just keeping everything in a text file. Just is easier. It's not gonna take too much size of the hard disk either. Anyway, let's go. I guess demo here. This is the data set I have. It has 8 inputs. This means I have to create a neural network with 8 neurons with no activation function in the input layer. This is 5, 6, 7, and 8. This is going to be x1, and the last one is x8. Yeah, 8. And then it has also 2 outputs. This means the last layer needs to have 2 outputs. Here, whatever I have is called hidden layer, and it's up to you or up to me here how many hidden layers I want to have. Okay, so this is the output 1, this is the output 2. What I know so far from the data set is the outputs have the type of floating point values, and they're all positive values, and also they're continuous values. This means the last layer's activation function, these two, must be either linear or even better to have the other one, which is called ReLU. You can just search on the internet this activation function, and then when you check the plot, you're going to see for the inputs less than 0, it's going to be always 0. For higher than 0, it's going to be a positive. It's going to be linear. Why I'm saying this is enough also, this is better than linear, because if you check out the data, you don't see any negative numbers on the outputs. This means we don't expect any negative values. Why we don't use just a regular, but it's up to you. Linear is going to work also as well. But what I cannot use is, for example, tangent hyperbolic in the last layer, because tangent hyperbolic is going to have negative values as well. The model is still able to train itself to show us the positive values, but the output is limited between -1 and +1. But if you look at data I have here, the data are not limited between -1 and +1. This means this activation function is not going to work unless I normalize this data to be between -1 and +1. Anyway, we don't want to do much processing on data, so we're going to just use linear. If you do this normalization so that the outputs would be normalized between -1 to +1, it's better. Probably the model is going to be trained better, but we're just going to try keep it simple as much as possible here. Anyway, so right now I know I have 2 outputs, 8 inputs. This is my first layer. Let's call this first layer, or I can just call it input layer. And this is my last layer. This is my output layer. Okay, and this is the way I can pass the number of layers I have and the neuron in each layer. For example, in the first layer, this 8 means I have 8 neurons, I have 8 inputs. For the last layer, I have 2 outputs. And this is the way I create it. For something in between, this is going to be my hidden layers. For example, right now I have 2 hidden layers, or right now I have 3 hidden layers. This architecture right now means I have, maybe I can just do it with another color. I have 32 neurons here. Then I have 16 neurons here, then I have 8 neuron here as well. Okay, this is the way this is the architecture of this model at this moment. Maybe I can just do it a little bit cleaner. And then all these neurons are connected together. Again, I don't want to go through the details of this, how this works. Essentially, the last layer is going to be connected to, well, this is already connected. Okay, what we have here, 8 actually neurons, 3, 4, 5, 6, 7. All these things are connected together. Okay, I don't want to go to the details, but this is details of how this is programmed, because I hope you already know the basics before you're watching this video. Then we have training split. What is the percentage of the data I want to use as training the model? And this coefficient means 0.8 means I'm going to use 80% of the data to train the model, and the rest is going to be for testing. Again, this is just not actually validation, it's called testing the data. The batch size in every epochs, how many samples I want to use to train the model from this trained data set. Learning rate, something we use, one of the parameters that we need to specify in SGD. You need to go read the formulation from this book, read the formulation, how the training the model works. One is evaluating the output, the other one is training the model based on how much is different from the expected value. This is learning rate, the number of the epochs, how many iterations I want to train on data set, and then this is how many times in every epoch I want to print out the results. If I do, let's say 2, it means every 2 epochs print the results. The type of the outputs, this one and this is the second one, the type of the outputs based on what I have here is continuous. You have 3 options: continuous, binary, and categorical. Right now we're doing continuous. In the future I might record another video for the other test cases we have. Anyway, right now this is the type of the output is continuous. It's not binary, it's not a classification, it's a continuous value. And then this is the data set, the same data set I have here. I already downloaded the file. I have the file here. I want to read the data. This is the file name. I want to read the data. Do I want to shuffle the data? Do I want to standardize the data? These are a little bit pre-processing the data. Sometimes you need to do that. Again, why we need to standardize data and why we need to shuffle the data, you need to know a little bit about the basics of artificial neural network, the data we're going to pass to a neural network. Right now, just a simple explanation, the range of inputs, for example, this x1, you can see the values are kind of between 0 to 1, even not 0, even like maybe bigger than 0. But the other output I have, x2, you can see the values are around 500 something, and the range is quite different. I want to standardize the data for each input so that they would be some value between, let's say, 0 to 1. This creates a more stable data set, and the neural network is able to kind of evaluate the outputs. If I don't do that, because some of the inputs are small, some of the output are too high, and then the weights are going to be multiplied by these inputs, if you know how this formulation of neural network works. And then through the back propagation, some of the values are going to become too much high, and then it's going to surpass the limitation of double, let's say, precision. It's going to, the value, the number is going to be too much high, and then you're going to see NaN results in the output. This is something that it's necessary to be done. And then after training the model, I want to save the model on the hard disk. Right now, the way I programmed this library is to save all those weights and biases which I trained on a text file. You can change it in any way you want. And then I want to use 6 threads when I am computing. I want to do it a little bit faster using prior computation. If I want to use only 1 thread, I can just change it to this one. Maybe we can just right now keep it on 1. Then about the activation functions, I have, well, the input doesn't need any activation function. The first hidden layer, second hidden layer, third hidden layer, and then the last one. So this is the second layer, third layer, fourth layer, and fifth layer. Let's go back to the activation functions, the way we set up the activation functions in this library. Right now, I want to say the second layer, all of them are going to be tangent hyperbolic. Let's go back to this. Not really quite good figure, a little bit messy, but I want to say all these neurons are going to have tangent hyperbolic activation functions, as well as this one, as well as this one. This value shows the proportion of the tangent hyperbolic. If I change this one to 0.5, still, because only one type of activation function is, this proportion is going to be normalized, and then essentially this means exactly the same as like all the neurons are going to have the same activation function. If I change this one, let's say, to something like this, and then I can say, let's say 50% is tangent hyperbolic and 50% is, for example, sigmoid. Then yes, there's 2 activation functions and 50% of that one. Or in another word, I can say, let's say 1.5. Okay, this proportion is going to be normalized. This means 75% of the neurons are going to, in this layer, are going to have an activation function of tangent hyperbolic, and 25% left are going to have sigmoid. We're going to run some test cases to show you that. But right now, let's keep it simple. All the hidden layers are going to have tangent hyperbolic, and the last layer is just going to have hidden layer. The setup for activation functions, I have to manually give the numbers. You can in the future change this one in a way you want that. Right now, the different types of activation functions I have in the first hidden layer or second layer is 1. If, let's say, I had here sigmoid, then I should have said here, I have to say it's 2. 2 types here, and then 1 type here, 1 type here, 1 type here as well. This is the way I give the inputs for activation function setup. It's not quite user-friendly, but C is a little bit, you have to do the things manually. But in the future, again, you can change it in a way you want. Let's forget about these comments at this moment. This is another setup for activation function we're going to try. We're going to read the file, the name of the file, which is energy efficiency data text file, is going to be read into a 2D array, and then we're going to decide if this data needs to be shuffled. If this is true, the data is going to be shuffled. And then we have a split data function. It's going to split the data into train, and this is not again validation, this is actually test. Right now, just it's the naming different. You can change the naming, doesn't matter right now, but it works exactly the same way. Anyway, I'm going to split the data into train and validation. Remember that we said, I guess it should be training and output. We said that training is going to be 80% of the data set is going to be used for to be used as train, and 20% is going to be test or validation. Now I'm going to deallocate the memory for the data itself. This is the way I wrote the function, but you can use pointers to point at the specific rows of data, and then you don't need to create another copy of the data on the memory if it's necessary. I'm going to standardize the data. I told you why I need to do that. I need to have to increase the stability of my multi-layer perceptron. I need to do that because the range of the inputs were quite different. I create the model, the multi-layer, this model, using that function, and then I print out the summary, I train the model, and then I save the model on the hard disk, and then I just wanted to show you that you can reload the model. This part is unnecessary. You can reload the model and you can train the model with a new setting, with a new learning rate, specifically in this example with a new learning rate and 2 more epochs, and then train the model and then free up the memory for the model if you want. Anyway, if I guess we have it. Okay, I can use this terminal. If you want to use the VS Code, feel free to use this VS Code. But if I just, maybe I didn't say, okay, this is the makefile I have. These are the source codes. Essentially, I'm going to create the object file sample. So this means I just need to do the make. And now the sample is created to train this data set with this architecture of artificial neural network. If I do this, this is what you're gonna see in your terminal. Okay, so we'll read the data. The number of samples means how many samples I have. Each row is 1 sample. I think you already know that. The number of features is the number of inputs and the number of outputs in total. So in total I have 10 features. 2 of them are targets. 8 of these features are input values. The data is shuffled. I passed through for the Boolean parameter shuffling the data. So I shuffled the data. I split the data into train and validation. 80% of this data, 80% of these samples are going to be used for train, 20% for validation, and then inputs are standardized. I needed to do that. I'm going to show you the difference if you don't do that. And then linear activation function. Okay, this is a summary. This function, after creating the model, this is the way I get the summary of the model I just created. So layer 0 means the input layer, the first layer. I have 8 neurons, and then the number of trainable parameters, I don't have anything to train in the input layer. There's no activation function. In the second layer, I have 32 neurons. Remember this architecture, this is my second layer, and it has 288 parameters. The summation of all the weights, every neuron here is gonna have 8 weights plus 1 bias. Okay, so every neuron actually is gonna have 9 parameters to be trained. 9 times 32 is the number of the parameters I need to train for this, for this, only this hidden layer, or you can say the first hidden layer. Just remove this. Okay. The activation function in this layer is tangent hyperbolic. The second, then I have the second layer. I have 32 outputs from this layer. This means every neuron here is going to have 32 weights plus 1 bias. So 33 times 16 is the number of parameters, the total number of parameters I have in this layer to train. And also the activation function for each neuron is tangent hyperbolic. Then the same scenario for the next hidden layer, which is this one. Then the last layer has two neurons, one this, one this. The same way the number of parameters are calculated, and the activation function for the last layer, these two are just linear because I want to predict linear or continuous values. The total number of parameters I need to train is 970, and then training model is initialized in this function. And then the batch size 32, this is the setting I passed to train this model. Batch size, number of epochs, learning rate, print every one, and the metrics used to compute the efficiency of the model in each epoch is continuous. This is mean squared error. This is mean the average absolute percentage error, mean average percentage error. This is the metric. These are the metrics we use for continuous outputs. And by just specifying the type of the output, automatically everything is going to be assigned, so you don't need to be worried. Did I change anything here? Wow. Okay, this is just one. The train. So the training starts for epoch, first epoch. These are quite large. This is too much high, the mean absolute percentage error for the output. How this matrix works, you need to know again the basics of the neural networks. Essentially, after 20 epochs in training my model, I reach to this mean absolute percentage error on validation data set, or in other words, this is actually test data set. After this training the model, I save the model with the file save, and the file save, if you remember, it was model text file. Let's go back here. I save the model on the current directory. This means I should have a text file called model. So if you open this, technically the weights for each layer and each neuron are going to be saved here with double precision. And the last one, yes, where am I? Okay, you can read this one later. Then I reload the model just by passing the same name. I free up the memory, I reload them. Let me just show you the results in the output. I deallocate the memory for the model I created, and then I load the model from this file, and then after reloading the model, I can retrain the model. Again, this is why when I start retraining the model, you can see already the validation is close to this one, because model was trained so far, already the weights and outputs were close to this percentage, and then I'm just doing more iteration to see if I can improve the model's accuracy, or in this case, decreasing the errors, deallocating the memory, and deallocating data memory for the data set. I have to run the model multiple times to see this is the best I can get. Let's just do one time and then creating the model again, running the model again. Seems like this is the best right now we can get. Let me see if there's something. I can just change this one, which is just going to use, technically every CPU has 2 threads. Technically I'm using 3 CPUs. The rest, there's no need to change it. Let me just run the code again. Well, there's not much to improve the percentage of rows. This one, Already it was good. There was no need to do another 2 iterations to improve the accuracy. This is the result I get from using scratchANN library with this library in C. What we want to do, we want to compare the results with what we have on TensorFlow. So this is the result we got on maybe just one more time. Right, so this is the best result probably we could get, like 8%. Yeah, this is, I'm sure this is the best result we can get for with this architecture, multi-layer perceptron. Anyway, I loaded the data and I saved the data in this format. Here I just wanted to know how many CPUs I have. So because TensorFlow is going to use all the available resources, so I assume we have 2 CPUs, 2 times 2 threads per CPU, 4 threads is going to be used. I just wanted to see what's happening. Then I split the data with test, which is 20%. Technically, I give the train and split here, but here in this format of splitting this function is like you give the proportion of the test case, but it's the same. So 20% for test. Here I'm just saying 80% for train. It's up to you. Shuffle the data. Here I didn't shuffle the data. Maybe I can shuffle the data too. Oh. So let's just shuffle the data. And then same architecture we had here. Tangent hyperbolic for all the hidden layers. And the last layer is just going to have linear with the same number of neurons. First one 8, 32, 16, 8, 2. We have the same things here as well. The shape of the train, if you just print this out, you're going to see this, the first one automatically. You're just directly passing the shape of the input, which is 8. Then we're using SGD. We don't have this option on scratchANN. Only we have just one algorithm, which is this SGD algorithm. So automatically it's going to use a scratchANN and automatically it's going to use this optimization algorithm. The training rate is also the same. The loss function is mean squared error, which the same thing, mean squared error we are using. And the metrics I want to be printed out is mean absolute percentage error, the same thing we have here. If I run this model, this is the result. This is the summary of the model I'm going to get. 975 parameters needs to be trained. The same thing we have here. We created exactly the same model. Exactly the same thing. The algorithm, everything is the same. Some minor differences might be here, but technically it's both exactly the same. And then the number of epochs to train the model. The number of epochs is 20. We use 20 as well. The batch size is 32. And then, again, this is not validation technically. This is the test dataset, but it's just the name is different. If I run this model, this is the result I get. The loss function after 20 epochs, or epochs, I don't know how exactly to pronounce that word. After 20 epochs, the mean square root is 32 here on Python, but here is a little bit much better actually. Mean absolute percentage error for train data test is here 9.5, around 10%. Here is around 15%. On validation, or we can say test, we have 34%. 34, the value is quite large, but here is around 8. The other one, mean absolute error, is around 9%. Here is around 14%. Why is scratchANN is working better? The only difference I because I implemented exactly the same thing we have in TensorFlow. Maybe we can run, if you run multiple times, actually if you run again, you're retraining the model which already was trained. So you have to one time recreate the model, and when you recreate the model, all the weights and biases are going to be reinitialized. And then when you start training, you're training the model again from scratch, technically from the beginning. If doesn't matter how many times you run it, it's I think it doesn't improve much. You can see it's kind of the same situation. If I click without rebuilding the model, if I click on here, it's going to retrain the model. The model which was already trained for 20 epochs, the model is being retrained. It's the same effect we had here. So we save the model and we retrain the model for 2 more epochs. Here I retrained the model on Python for 20 more epochs. Anyway, so you have to, if you want to have produced the same kind of concept we have here, you have to, we're comparing with the first time training the model. Anyway, the only reason I see that, because SGD is the same, I implemented the same training algorithm. The only reason I see that the results is different and scratchANN is working better is the way I am initializing the model. I'm not sure exactly that's the reason, but I assume that's the only reason why scratchANN is working better. Going back to scratchANN, this is the way I initialize, this is the function I initialize the weights and biases, and I'm using Lipsodium library, this library, and this library is quite efficient in terms of initializing, in terms of giving you a random number. It's much efficient, more than probably, it's used also in cryptocurrency, which you need a highly efficient random value. There's no other reason I see, but let me know if you figure out why the scratchANN in this particular point is working better than the Python TensorFlow. There are some disadvantages also scratchANN has. Let's say if I change this one to linear, let's just not even that one, maybe I can just this one. And now if I again, don't need to clean it, sample, you're gonna see a bunch of NaN results here. Maybe I can just decrease the number of epochs to 2, and then again, and if I go back to the model I just saved, you can see all the weights are also NaN. Maybe I can change, I want to show you something. Let me see. So instead of just small proportion of maybe 7, because last layer has 8 neurons, I'm saying 7 of them should have tangent hyperbolic and only 1 of them should have linear, and this means the last layer has 2 configurations here. I have 2 configurations, and if make again, I want to decrease the number of epochs as well, and then make again, sample. Well, still it's giving me this problem. I just want to see what would be, yeah, still it's linear, and all the 2 neurons, both of them are going to have the same issue. So the problem is, I don't know how this library, this TensorFlow can handle this. When I know kind of but I was too lazy to implement that. But when you run this, it doesn't give you an ANN. The problem in my code in scratchANN is when the back propagation is happening, because it's linear and the output of linear, the output of each one is still going to be a linear value. So we can say if this is the activation function, the input goes in and the same input is going to go out, and then this, when it goes to the next neuron, is going to be times another weight, and every time the output is going to be times another weight. And when the backpropagation happens, when this weight goes higher and higher, this quite large value is going to be times another large value, and essentially this is going to be higher than the limit of the double precision. You can handle this if you want to improve the scratchANN, but somehow I don't know exactly what is the implementation behind this TensorFlow to handle that, but definitely there's a way you can do it in a scratchANN as well. In another way that, let's say I don't standardize the data, okay? In TensorFlow, it shows this is a limit that TensorFlow can handle unstable the data sets, as well as especially when it comes to the linear activation function. When you're not using linear, every time again it's going to be times another weight, and when the weight is too high, this is going to be too much big value. But when you're using a tangent, let's say this is Z, and then the output, I don't know, let's call this Z1, let's call this Z2, and this one, if it's a tangent hyperbolic, Z2, the output of the neuron, Z2 is going to become a value in between -1 and +1. So +1. So this value, the output of if each neuron is going to be limited. But when this output is not limited, it can go quite large with no limit, and then times another large value. Essentially, this problem is going to happen. But the same issue is going to happen, let's say, if I don't normalize the data and then creating the model with all activation functions linear and then training the model. You can see also the TensorFlow has a limit to handle the instability on data as well. So this is why I'm getting NaN, also TensorFlow is getting NaN, but definitely the model in TensorFlow is more robust. Another way to solve this problem using another optimization algorithm, if I change this SGD to Atom, you're going to see this is going to work. But in scratchANN, we don't have Atom. You can develop it, of course, in the future if you want. Let's try. Well, let's do it maybe. Let's go back to all tangent hyperbolic, the way it works. And also, I want to change this to ReLU activation function. I want to standardize the data. Okay, this is the model I just created, and then when I do the ReLU, still it's gonna work. Maybe I was expecting to have a little bit better results. Let me see. Well, not necessarily, but let me just do it one more time. Okay, I guess this is the best result we can get with ReLU. It's weird, should be maybe a little bit better. But anyway, we can do the same thing here. Shuffling the data, standardizing data. Here, I don't want to use any linear because again, the error is gonna, not the error, the value can go quite large. The last layer, I want to have one of the activation functions to be linear and the other activation function for the other neuron is going to be ReLU. So in another word, if you go back here, this means this is going to be linear activation function. This one is going to have a ReLU activation function. So this is just a setup for the last layer, and it has this config size has two types of the sizes too, and then I guess the same should be the same. The rest should be the same. If you make again, run the code, this is what I get. Of course, I want to have a little bit more. Make maybe, yeah, and the sample. Well, here is not getting better much neither. Maybe we can just, if I want to change it to use only a ReLU activation function, I can remove this one, set this back to 1. Well, yeah, mine is not actually getting better much neither, so I guess it is what it is. So let's try another setup for activation function, because this is a feature you have only in scratchANN, and I was thinking maybe I can show you the potential for scratchANN to change different configurations for activation functions. This time I'm going to have 3 different activation functions in the first layer. 3 different activation functions. Okay, and I'm saying 20%. This is the ratio, of course, the ratio of the linear activation function in the first layer. Essentially, we're going to see the percentage, but this is the way you can calculate. This is going to be the percentage of the neurons which have linear activation functions inside the first hidden layer, or in other words, second layer. And then the third layer is going to have just tangent hyperbolic activation function. This layer, which has 8 neurons, 5 of them are going to be sigmoid, and 3 of them are going to be tangent hyperbolic. And then the last layer, which is this one, one of them is going to have a value and the other one is linear. This is the way I set up the configuration. I have 3 different activation functions here. The size is 3. The size of this one is 1. The size of this one is 2. 2 different setups for activation functions. Here I also have 2 different activation functions. Essentially, I pass all these configurations to this activation function pointer, because then this is the way, this is the array is going to be used when I'm creating the model. Each neuron is going to have an array of weights, bias, output, as well as a pointer to an activation function and a pointer to derivative of the activation function, which is used in backpropagation. But let's go back here. Okay, we changed the configuration, and now I want to see if this is, maybe I should clean. Okay, and then I want to run the program. Okay, now I can see a little bit actually the result did improve. I have different setups for activation functions in layers. You can see after I print the summary, the total number of the parameters is the same. I didn't change anything about the total number of the parameters. It's the same as the other model we had. But the percentage of the activation functions linear is like around 22%. The tangent hyperbolic is 50%. The other one is 28%. You can just do the math and see how many neurons are used for linear. About the last layer, 50%, which in this case, we're talking about only one activation function, is used, is assigned to be linear, and the other 50%, which technically, again, just one extra, the other neuron we have in this layer is going to use this activation function. About this rest of the settings to train the model, everything is exactly the same. I trained the model, and this time I can see the result is slightly better. The choice of activation function is completely up to you. It depends on the model itself. It depends on the data set itself, that if it wants to capture a linear or non-linear connection between the inputs and the outputs. The other one, let's say this one every all the hidden layers were having linear activation functions. In that case, maybe it was not working because specific for this data set, the model requires to see more non-linear connection between the inputs and the outputs. But here we used a mixed activation functions, which again, it's better than the tangent hyperbolic, all tangent hyperbolic in the hidden layers than just one linear in the output. I assume this specific data set we have, energy efficiency data set we have, has both the linear and non-linear connections between inputs and the outputs. Anyway, let me know what you think. If you have any questions, feel free to reach out. In the future, probably I'm going to record more videos about more different data sets. This one was energy efficiency data set. Probably in the future, I might do test case study for breast cancer. Also a little bit more challenging data set, which is quite larger than the other one. The model is going to be larger. It has 784 inputs. This model we just did had 8 inputs, but this one again has 784 inputs, and also the output is a classification, and we do the one hot encoding. So essentially it's going to be the output layer is going to have 10 different outputs that we need to predict. Thank you for watching this video. Let me know if you have any questions.